Hi guys, this is going to be a very brief video on how to use the Arrhenius equation to solve for either the ratio of two rate constants, the temperature for K1, the temperature for K2, or you could alternatively use it to solve for the activation energy for a particular reaction. You get this equation by taking the Arrhenius equation that you might be familiar with from chapter 14. This is the rate constant for the reaction, which is equal to this thing called the frequency factor at times e to the negative of the activation energy divided by R, the gas constant, times the Kelvin temperature. And essentially it works like this. If you raise the temperature, what you wind up doing is you wind up raising the rate constant. And if you raise the value of the rate constant, you raise the rate of the reaction. Now we can compare two different rate constants by simply subtracting the natural log of, let's say, the rate constant for a reaction at one temperature minus the rate constant for the reaction of the other. And what that gives us using log rules is the log of K2 over K1 in this particular case. And all you're doing is you're taking the natural log of both sides of this reaction and then you're subtracting one from the other, and you get either of two versions of the equation. So one version is the natural log of K2 over K1, ratio of the rate constants, is equal to the negative E of A over R times the difference between the inverse of the second temperature and the inverse of the first temperature. Anytime I can get rid of negative signs, I'll simply multiply them through a set of parentheses. I did that in this case, which got me out of the negative sign in front of E of A, but it reversed the inverse temperatures. So you can see that the only difference between these two equations on the right hand side is that this is 1 over T1 minus 1 over T2, and it got rid of the negative sign here. But either one of them, they're both the same equation, just rearranged in what I think is a little bit easier to use. All right, so here we go. So in this particular problem, we've got this reaction for the decomposition of butane into 2 moles of what appear to be ethene. And actually, this is butene to ethene. And what we've got is we've got an activation energy of 262 kilojoules per mole. And that's right up here. So this is 262 kilojoules per mole. Now, you're going to have to use the version of the gas constant, which is 8.3145 joules per mole Kelvin. And we want to get them into the same unit. So we can either divide the gas constant R by 1,000 to get it into kilojoules, or we can go ahead and multiply the activation energy by 1,000 to get it into joules. And let's just go ahead and do that. It's pretty simple. We're just multiplying by 1,000 joules per kilojoule. Kilojoules is going to cancel, and that's going to give us 262,000 joules per mole. Hopefully you can see that. I know it's kind of up there in that bar right there. All right, so we've got our gas constant, we've got our activation energy, we have the temperature, which is for K1, that's the lower temperature, and the temperature that's for K2, that's the higher temperature. All right, and so what we're going to do is we're going to plug those values in here. So let's go ahead and do that. That'll give us the natural log of K2 over K1. Okay, and that ratio is equal to 262,000 joules per mole, and that will be divided by 8.3145 3.5. Most people just round that to 0.315, but we'll be a little bit more precise. And that's joules per mole Kelvin. And I really apologize for the handwriting. And then this is going to be 1 over T1, which is the lower temperature because I don't have the negative sign out here. So it's 1 over 600 Kelvin minus 1 over T2, which is 815 Kelvin. Let's take a quick look at the units. Joules will cancel. Moles will cancel. And this is the inverse of Kelvin, 1 over Kelvin. This is 1 over 1 over Kelvin, which is equivalent to Kelvin over 1. So the Kelvins will cancel as well. All right. So if I plug all of that in my calculator, here's what I get for the natural log of K2 over K1. I wind up with 13.85. Now to get rid of the natural log, I'm going to take the E of both sides of this expression. When I take the E of both sides of the expression, I wind up with a ratio. I'll just put an arrow out here. This is the ratio of K2 over K1, and that's actually equal to 1.04 times 10 to the 6th. That is the ratio of K2 over K1 after taking the antilog E of the natural log 13.85. What this is telling us is that this reaction, by raising the temperature from 600 Kelvin to 815, that's only a 215 Kelvin difference. What I've done is I've increased the ratio of my rate constants by 1,000,000 times. And that's just a little bit of a temperature increase, which gave me 1,000,000 times the rate rate for K2 over K1. Now, since K2, so what we're interested in here is we're interested in the value of K2, and since K2 over K1 is equal to 1,000,000, or 1.04 times 10 to the 6th, we can solve for K2 by simply multiplying K1 times that ratio. It's just times the ratio of K2 over K1. And so that's just going to be, here's K1, it's given in the problem, 6.1 times 10 to the minus 18. So that's 6.1 times 10 to the minus 18. This is first order, it's in per seconds. And we're going to multiply that times the ratio we just determined, which is 1.04 times 10 to the 6. And when I do that, I get 6.3 times 10 to the minus 12 per second. And that is my value for K2, which was what was asked for in the problem.